The internet crashed yesterday, not really sure why, but I'm going to continue to do what I was doing yesterday, is reviewing the resources that I have about network. And probably I'm gonna try hardware as well, but we'll see how long it's gonna take to review the network stuff, network related stuff. I think I might go over this stuff here as well, which is related to type theory. Probably this one, but the issue with this one is that there's so many links here. So it's probably gonna be open up a bunch of tabs on the sidelines. And kind of the issue with this is that I usually like to go over all of them so I don't have too much stuff open as I work on a bunch of other things. So I'm not really sure if I should do this now or if I should complete the other stuff that I have to do first. So I'm not really sure if I'm gonna do it. I'm gonna begin by reading the last GPT or last Gemini response and then last ChatGPT response. Actually, ChatGPT, I open a new tab. Apparently, based on the Teal's video, they are gonna record everything. Like they are forced to record everything because of a law that somebody passed. Which obviously, even if the law wasn't passed, is already like expected that they're gonna get the data, which is obviously very bad. Obviously, I'm against all of this, but not sure if there's much that we can do. And the best you can do is to, if I had the hardware to run local LLMs, I definitely would do that. But the issue of running your own is that you need a lot of GPU to have fast inference. So I don't have right now the necessary stuff. So I'm gonna have to compromise and just use their stuff until I have enough GPU to run my own thing. Fine.
And driver. In the world of computer networking, the network interface card, NIC, and its driver are a fundamental duo, working in perfect concert to connect your computer to a network. While they are inextricably linked, their responsibilities are distinct. Think of the NIC hardware as a highly specialized, physical instrument, and the NIC driver as the skilled maestro who knows exactly how to play it. What the NIC hardware is responsible for, the physical work. The NIC is the physical circuit board or integrated chipset that provides the tangible connection to the network. Its duties are grounded in the physical and electrical realities of data transmission. Exactly what the hardware does. Signal conversion, this is its most fundamental role. The hardware converts the digital data, ones and zeros, from your computer's memory into electrical signals for transmission over an Ethernet cable, light pulses for fiber optic cable, or radio waves for Wi-Fi. It performs the reverse process for incoming signals. This is a physical layer, layer 1, function in the OSI model. Physical connection, it provides the physical port, like an RJ45 Ethernet socket, or the antenna to physically connect to the network medium. MAC addressing, every NIC is permanently encoded with a unique media access control, MAC, address from the factory. The hardware uses this address to identify itself on the local network, ensuring data packets are sent to the correct physical device. This is a data link layer, layer 2, function. Data buffering, the NIC has a small amount of onboard memory, a buffer, to temporarily store incoming and outgoing data. This helps to manage speed differences between the computer's fast bus and the potentially slower network. Basic data handling, the onboard controller chip handles the fundamental encapsulation of data into Ethernet frames, including adding the MAC header and a trailer for error checking, frame check sequence. Link and activity indication, the familiar LED lights on an Ethernet port are controlled directly by the hardware to provide a visual status of the network connection, link, and data transmission, activity. Hardware offloading, advanced NICs, more sophisticated NICs can perform tasks directly on the card to reduce the load on the computer's main CPU. This can include checksum calculations or segmenting large blocks of data for TCP segmentation offload. What the NIC driver is responsible for, the software control. The NIC driver is a specialized piece of software that acts as the essential translator and manager, allowing the operating system to communicate with the specific NIC hardware without needing to know the intricate details of its design. Exactly what the driver does. Translation and interfacing, its primary role is to be the intermediary. It translates the generic networking commands from the operating system, example, send this data packet, into the precise, low-level instructions that the specific model of NIC hardware understands. Data formatting, the driver takes network packets, like an IP packet, from the operating system and formats them into the proper frame structure that the NIC hardware requires before handing it over for transmission. Interrupt handling, when the NIC hardware receives a packet from the network, it generates an electronic signal called an interrupt to get the CPU's attention. The driver is the software that catches this interrupt, retrieves the data from the NIC's buffer, and passes it up to the operating system's networking stack for further processing. Resource management, the driver manages the NIC's resources, such as its memory buffers, and controls the flow of data to and from the card to prevent it from being overwhelmed. Configuration and control, the driver exposes the NIC settings to the operating system, allowing a user or system administrator to configure options like link speed, example 1 Gbps, 100 Mbps, duplex mode, half/full, and wake on LAN. Status reporting, it constantly monitors the NIC's status such as whether the network cable is connected or disconnected and reports this information back to the operating system. Standardization. Drivers are written to conform to standard interfaces, like NDIS in Windows or standard kernel models in Linux. This allows the operating system to interact with any NIC from any manufacturer in the same way, as long as the correct driver is installed. In short, the hardware is the physical tool that does the work, but it is inert and useless without the driver. The driver is the intelligence that tells the tool exactly what to do, how to do it, and when, all while seamlessly communicating with the broader operating system.
So something that it wasn't very clear for me when I was first learning about all this stuff is it's still not 100% clear. So I'm gonna try to clarify more now. But it's basically the conflict that you get, because if you think about it, obviously there's gonna be several different computers communicating with each other at the same time. So how does the system overall knows what is a frame? So like if you have two different computers sending data at the same moment, like wouldn't the bits from one computer interfere with the bits from the other computer and then like crash the system basically? And this part is still not very clear about the nuance, but basically on a general level, the way that it works is with a preamble pattern. So the frame has like a sequence of bits before and sequence of bits after the frame, and that's how the router is able to know when to initialize like the algorithms inside of the router that are gonna process the frame. But obviously it's still not very clear, because then like how does it know what is the exact moment? But I think it's just based on like error and frequency. So it's not that it works 100% of the time, it's that the amount of errors that happen are not significant enough to make the network very slow. So I think that whenever it fails to parse the frames correctly, it just drops the packets, and then the client or the server sends the request again. And the way that it works is that the router or switch, they only send one frame at a time. So it's kind of like waiting, putting the packets on a waiting line, and then they send frame by frame to the destination. And the way to think about the routers is that it's not only like hardware, it's just like a computer. So routers have operational systems as well, as far as I understand. And so there's a lot of code you can put on the router and across the paths. But mostly what they're gonna do is just keep track of a hash map of the hash map is basically the bridge between the points that the router is connecting. So the easiest way to think about the network is just a bunch of hash maps distributed across all these devices that have these protocols that are gonna allow the devices to synchronize, and after the synchronization, encrypt the data, so that nobody can figure out what are the messages. So let me ask about. I'm gonna. This is the other thing that I was gonna ask right now, like this stuff that I was thinking about yesterday, which I kind of get it, but not really. So I'm gonna ask now, which is what is the purpose of the cyclic redundancy check, and how does Manchester encoding works? I might be overly complicated in my mind, this stuff, but I still obviously want to clarify as much as I possibly can. The Manchester encoding is one of the algorithms that I was talking about last time, which the purpose is to recover the clock cycle on the other end, or to know. This is the part that is not very clear to me. But I think like you need to recover the clock cycle, because that's the only way you are able to parse what is considered to be a 1 and what is considered to be a 0. And obviously you're gonna need to know, or to make sense of the data that is coming in. So the way that this Manchester encoding does this is by, I think it's sort of like merging the two, the clock and the data. But this is the thing that is, I guess, not very clear, because what exactly is the data in this context? If the purpose of the recovering the clock was to figure out what is a 0 and what is a 1, what would be the data if you didn't have the clock? I think that's probably the question to ask. But basically, the superficial answer that I got yesterday, I think, is the Manchester encoder is just gonna make it so that it's a circuit that delays the incoming signals based on a phase value, let's say, and this allows the system that this is connected to capture the edges of the clock. So you can think about like a buffer, a waiting buffer. You have the external system, then a waiting buffer, which is basically a clock. It works based on a phase shift, and this is connected to the internal system. The signal comes, it goes into the loop of the phase shift, which delays the signal by a necessary amount, by a standard amount, that allows it to like pass the correct information to the rest of the circuit. That's how I'm thinking about it right now, but I'm gonna ask more questions to try to clarify. So, the other thing that I wanted to do, I'm gonna review these ones now. And these are the images from the Understanding Linux kernel, which I vaguely remember. This is another problem, is like too many details that you, even though like I already studied all this stuff a bunch of times, you kind of forget the details of everything. But it's becoming a lot more clear. I think that I overly complicate on my mind, because I want you to understand all the details, and it's confusing to think about the hardware and the relationship between the hardware and the software. But if you study the Linux source code, it's probably not that complicated to understand. But Linux, I think, has this SKB, which is kind of like a library that manages the sockets, and obviously it's going to be related to this low-level communication stuff. So the book, they have a bunch of pictures that shows like the control flow of this SKB. It's basically the way that the kernel manages the sockets. Another thing that is more clear now, after yesterday, that I revealed some of this stuff, is that the OS is going to be the thing that manages the memory. So the NIC is the physical layer. So it resolves the IP to MAC, I think, translation, and it implements the clock, the cyclic redundancy check, and it basically parses. It basically checks on the physical level, like the lowest layer. I think it's layer 1 and 2, so it's physical, and the other I think is data link. It basically verifies that the frame is in the correct format. And it depends on the situation, but I think most NICs probably are gonna have some software. It's not the gates, specialized gates on the NIC. There's also some additional software to like help the workload. So remove the workload from the CPU because of the stuff that I was saying about yesterday, which is the bus. So you want to minimize interrupt requests so that the operating system can handle other stuff, all the processes that is running, without having to constantly check for the NIC interrupt requests. And that's what it is related to DDoS attacks, denial of service attacks, because obviously that's how it works. So when you have a bunch of requests being sent to the same device, it forces a bunch of interrupts on the operating system, and because everything is happening on the physical layer, there is no way. There's always this balancing act between the operational system and the processes that is running. Because obviously, when you have a process running, by definition, the operational system is not gonna be running. But ultimately, everything is the operational system. Like the operational system is the only thing that actually runs on the hardware level. You can think about every other process running as a child, like as a sub process as part of the code, the operational system code. So the OS is the container for all the code that it's going to run. But then when the process is running, the OS is not going to be running. So how does the OS figure out when to stop the process, like in order to prevent the process from running forever. And it's going to do that based on timing and based on these interrupts. So the interrupts is basically the essential principle of the computer. It's like the attention of what determines the attention switch of the computer. It's kind of like a notification on a website, for example. The responses.
Of course. Let's break down these two fundamental concepts of data communication. They serve very different but equally important roles in ensuring that data gets from one point to another accurately and reliably. The purpose of cyclic redundancy check, CRC. The primary purpose of a cyclic redundancy check, CRC, is to detect accidental errors in raw data. Think of it as a highly effective data integrity check. It's used in digital networks, like Ethernet and Wi-Fi, and storage devices, like hard drives and SSDs, to verify that a block of data has not been altered or corrupted during transmission or storage. How it works at a high level. Calculation at the source. Before a block of data, a frame or packet, is sent, the sender performs a mathematical operation on the data. This calculation, which treats the binary data as a long polynomial, is divided by a specific, predefined number known as the generator polynomial. The remainder of this division is a short, fixed-length value called the CRC checksum or simply the CRC. Appending the checksum, this CRC checksum is then attached to the end of the original data block. Verification at the destination, the receiver gets both the original data and the CRC checksum. It performs the exact same polynomial division on the received data using the same generator polynomial. Comparison. If the receiver's calculated remainder matches the CRC checksum that was sent with the data, it is highly probable that the data is free of errors. If the remainders do not match, it signals that an error has occurred during transmission, and the receiver can discard the corrupt data and typically request a retransmission. Key characteristics of CRC. Error detection, not correction. CRC is excellent at telling you that an error occurred, but it cannot tell you which bit is wrong, nor can it fix it.
So this goes into the stuff that I was saying about the routers. Because everything is connected on a peer-to-peer system, it's kind of like decentralized, but not 100%. So you have nodes that are authority nodes because of the DNS translation. But I think for the most part, it's going to be kind of like the ISP is the centralization point where everything converges because like the manager system. But between the routers and the devices, and when you introduce cloud as well, devices, it's going to be sort of decentralized. So because of that, you can have man-in-the-middle attacks where someone hijacks the path along the chain, the connection. So imagine like an attacker swaps the router for its own router in order to retrieve information. Then this is the purpose basically of these checks. You have both the checksum and this redundancy check, which is basically just making sure that no one fucked with the bits across the path. You can imagine if you introduce a bunch of bits or if you remove bits, the calculation is going to be off, which means that the packet is dropped. But obviously this doesn't fully prevent all the attacks because you can switch the bits without... I think that the cyclic redundancy check is harder to bypass, but the checksum is relatively easy because it just sums all the bits. It sums all the bits and does some other stuff, I think, to see if it's going to be equal to 0 or something like that. And it's easier because you can flip the same number, same amount of bits. So like you can change the nature of the message without changing the checksum, basically. But I think this one is harder to do this, but it's still not perfect. So there's ways to bypass. But then when you add encryption on top of that and all the other stuff, then it becomes a lot harder as well.
For burst errors, it is particularly good at detecting burst errors, where multiple consecutive bits are corrupted, a common type of error in communication channels due to noise or interference. Not a security measure, CRC is designed to protect against accidental changes from noise, not intentional or malicious alterations. An attacker could easily modify the data, calculate a new valid CRC for the modified data, and the change would go undetected. How Manchester encoding works. Manchester encoding is a line coding technique used at the physical layer, layer 1, of the OSI model. Its primary purpose is to solve a fundamental problem in digital communication, clock synchronization. It cleverly combines the data signal and the clock signal into a single, self-synchronizing stream. The core principle, transitions are key. Instead of representing a binary 1 with a high voltage and a 0 with a low voltage, or vice versa, Manchester encoding represents data using transitions in the signal. The rule is simple. There must be a transition in the middle of every bit period. The direction of this transition determines the bit's value. There are two common conventions. Original Manchester encoding, G.E. Thomas 0 is represented by a low to high transition in the middle of the bit period. 1 is represented by a high to low transition in the middle of the bit period. IEEE 802.3, Ethernet, standard. This is the more common convention in modern networks and is simply the reverse of the original. 0 is represented by a high to low transition. 1 is represented by a low to high transition. Example using the IEEE 802.3 convention, Ethernet. Let's encode the binary sequence 101. To encode 1, the signal must have a low to high transition in the middle. So, it starts low and transitions to high. To encode 0, the signal must have a high to low transition. It starts high and transitions to low. To encode the next one, the signal again needs a low to high transition. Since the previous bit ended on a low state, it can simply continue from there. Here is a visual representation. Bit 1, 1, bit 2, 0, bit 3, 1, underscore 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 dash 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 caret 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 low to high to low to high means 1 means 0 means 1. Note, transitions may also be needed at the start of a bit period simply to get the signal to the correct starting level for the required mid-bit transition. The main advantage and disadvantage. Advantage, self-clocking because there is a guaranteed transition in the middle of every single bit. The receiver can use these transitions to synchronize its clock with the sender's clock. This eliminates the need for a separate clock wire and prevents synchronization problems that can occur if there's a long string of identical bits, like 0, 0, 0, 0, 0, 0, 0, 0, or 1, 1, 1, 1, 1, 1, 1, 1, in other encoding schemes. Disadvantage, bandwidth inefficiency. The guaranteed transition means the signal has to change state at least once per bit. This requires approximately twice the bandwidth of simpler encoding schemes, like NRZ, non-return to 0, to transmit the same amount of data. For this reason, it's common in 10/100 Mbps Ethernet but not used in higher speed standards like gigabit Ethernet, which use more complex, bandwidth-efficient codes.
Yeah, I guess I don't understand. Like, I have a hard time understand this. Obviously, I understand if you have a message that only has 1 voltage. How do you differentiate, like, how many bits? Because if the voltage never changes, then obviously it would be considered as 1. Like, instead of 1, 1, 1, 1, like several ones in a row, it would be just 1. So it makes sense. But then, like, how does that different? Because it has to switch at some point. So I think that the protocol means that both sides are gonna force switches in order to represent the 1. I think that's what it means. So instead of sending the data only as high voltage, you send as transitions of the state. Yeah, that would make sense. I think that's the point. I guess I'm overly complicated on my mind. It's just easier. Like, one side makes sure that if it wants to represent several ones at the same time, it's gonna transition the voltage instead of maintaining the voltage constant. But if you have an internal circuit, it's probably different. Not really sure though, because it would be the same. I think internal circuits are gonna use UART clocks or UART transmission protocols. It's kind of like a network protocol, but it's a lot simpler. But it's the protocol used to determine communication between devices on the same hardware, I think.
Here's a direct, structured, and deep answer that gets to the core of your questions about CRC, Manchester encoding, clock recovery, and the metaphysics of what is the data being transferred, White heavy checkmark summary of core points. Cyclic redundancy check, CRC error detection technique that helps the receiver detect corruption in the transmitted data. Manchester encoding, a line encoding that combines data and clock into a single self-clocking bit stream. Clock recovery purpose, extracts timing information from the incoming data stream so the receiver knows when to sample the signal. If no clock recovery existed, the raw bit transitions would become meaningless because the receiver wouldn't know when to sample each bit. The data would turn into noise, timing drift, or framing errors. Philosophically, what is the data? The data is a sequence of state transitions, changes in voltage, light, etc., that only becomes meaningful after clock synchronization, framing, and decoding at higher protocol layers. White heavy checkmark detailed breakdown. Pushpin 1. What is the purpose of a cyclic redundancy check, CRC? Goal, detect transmission errors, example bit flips due to noise, interference, faulty cables. How it works. The sender performs a mathematical division of the data payload by a predefined polynomial, the CRC polynomial. The remainder of this division becomes the CRC checksum, appended to the packet. The receiver performs the same division on the received data plus checksum. If the remainder at the receiver is 0, rightward arrow data is assumed intact. Otherwise, rightward arrow error detected. What CRC catches? Burst errors, flipped bits, and other common transmission faults. Doesn't correct errors, just detects them. Why it's used? Lightweight, fast, good balance between detection power and computational cost, compared to cryptographic hashes or full error correction codes. Pushpin 2. How does Manchester encoding work? Problem it solves. In traditional binary encoding, like non-return to 0, NRZ, long strings of 1s or 0s can cause clock drift and loss of synchronization. The receiver doesn't know when one bit ends and another begins. Manchester encoding strategy. Every bit has a guaranteed voltage transition in the middle of the bit period. Encoding rule. IEEE 802.3 standard. For example, 0 rightward arrow high to low transition, upward arrow downward arrow, 1 rightward arrow low to high transition, downward arrow upward arrow. Effect. You get a self-clocking signal. The clock can be recovered from the transitions themselves because there is always at least one edge per bit. Trade-off. Manchester doubles the required bandwidth, since each bit requires 2 signal changes. Pushpin 3. Clock recovery. What happens if it didn't exist? Why it matters. In serial communication, only one wire, or optical channel, or RF carrier, is often used to send data. There's no separate clock line. What clock recovery does, it looks at the incoming signal's edges/transitions and derives timing signals from them. Example phase lock loops, digital clock recovery circuits. The receiver uses this recovered clock to know when to sample the data line. If it didn't exist, the receiver would sample at the wrong times, wrong phase, wrong frequency. Bit errors would explode. You'd get framing errors, random bits, drift. In short, you would receive garbage. Metaphysical summary, data transmission without clock recovery is like trying to read Morse code without knowing the dot dash timing. Pushpin 4. Philosophically, what exactly is the data being transferred? On the physical layer, what's physically transmitted is temporal state changes in some medium. Electrical voltage shifts, light pulses, radio frequency modulations, magnetic flux reversals, on disks. But meaning emerges only after multiple stages. Layer what it sees physical layer voltage transition/light pulses data link layer framed bits, packets/frames, transport layer packets, streams application layer files, messages, APIs. No clock recovery equals no meaningful bit stream. Without it, even the first step of parsing a 0 vs 1 breaks down. Ultimate conceptual view, data is not the physical signal. It's the abstract, synchronized interpretation of symbol transitions over time, given a shared protocol for timing, framing, and decoding. White heavy checkmark final thought. Your data doesn't exist as an independent thing in transmission. It only emerges after decoding physical events through layered human agreed rules, beginning with clock recovery. If you want, I can draw you a conceptual diagram showing how a physical signal progresses from raw electron/light to meaningful application level data. White heavy checkmark strategic questions for you. Are you more interested in digging deeper into error detection/correction theory, CRC, Hamming, Reed-Solomon? Or into signal encoding techniques, Manchester, 8B/10B, PAM4, etc.? Or clock recovery algorithms, PLL, DLL, CDR circuits? Or more the epistemological/computational philosophy about the emergence of meaning from physical state? Let me know which path you want next. Excellent questions. These topics cut to the very core of how digital devices work, from communicating with themselves to communicating with the world. Let's break down each one. 1. Why clock recovery is necessary, and why high/low voltage isn't enough. You've hit on a brilliant and fundamental problem in digital communication. The simple idea of high voltage for a 1, low voltage for a 0, a method called NRZ or non-return to 0, seems logical, but it has a major flaw. The problem, losing the rhythm. Imagine you are trying to read a long message tapped out in Morse code. If the sender sends a very long dash, representing a long string of 1s, or a very long pause, a long string of 0s, how do you know if it was 10 dots worth of time or 11? If your internal metronome is even slightly faster or slower than the sender's, you will eventually miscount. You'll either add or miss a bit. This is called clock drift. This is exactly the issue in digital systems. The receiver needs to sample the signal at the precise moment in the middle of each bit's time slot to read it correctly. Without a timing signal, it has to rely on its own internal clock. Even high-precision crystal oscillators have tiny variations. Over a transmission of thousands or millions of bits, a small difference in clock speed between the sender and receiver will cause the receiver to eventually sample at the wrong time, leading to errors. The solution, clock recovery. Clock recovery is the process where the receiver extracts the timing information directly from the incoming data signal itself. This is why encoding schemes like Manchester encoding were invented. By forcing a voltage transition in the middle of every single bit, Manchester encoding guarantees the receiver gets a regular pulse to synchronize its clock to. It's like the sender is tapping out a steady rhythm along with the message, so the receiver never loses the beat. In modern high-speed communication, like gigabit Ethernet or USB, more advanced encoding schemes are used, but the principle is the same. They ensure there are enough regular transitions in the data stream for the receiver's circuitry, often a phase-locked loop or PLL, to lock onto and perfectly synchronize with the sender's clock. 2. What is a UART? A UART, Universal Asynchronous Receiver/Transmitter, is a piece of hardware, a microchip, or a part of a larger microcontroller, that acts as a translator between the internal world of a computer and the external world of serial communication. Internal world, parallel inside your computer, data moves around in parallel on buses. For example, an 8-bit chunk of data, a byte, travels simultaneously across 8 separate wires. This is very fast but only works over very short distances, i.e., on a circuit board. External world, serial to send data over a longer distance, like to another device, it's inefficient to use 8 wires. Instead, we send the bits one after another down a single wire, plus a ground wire. This is serial communication. The UART's job. A UART's job is to manage this conversion. Transmitting, it takes a byte of parallel data from the computer's bus, adds a start bit, a signal to tell the receiver, hey, data is coming, sends the data bits one by one, adds an optional parity bit, for basic error checking, and finally a stop bit, to signal the end of the byte. Receiving, it does the reverse. It listens for a start bit, reads the incoming data bits sequentially, checks the parity bit, and once it has the full byte, it presents it in parallel to the receiving device's bus. The asynchronous part is key. There is no shared clock between the sender and receiver. They only need to agree on the transmission speed, the baud rate, beforehand. The start bit allows the receiver to synchronize its clock for the short duration of that one byte. 3. On motherboard versus network communication. This is a fantastic question that highlights the different engineering challenges of short distance versus long distance communication. How devices on a motherboard communicate. Hardware devices on a motherboard, CPU, RAM, graphics card, etc., communicate through a highly organized, high-speed system called a bus. Think of a bus as a multi-lane superhighway etched directly onto the circuit board. Characteristics. Parallel, data is often sent in parallel, example 64 bits at a time on a 64-bit bus, leading to massive bandwidth. Synchronous, all components are physically close and connected to the same master system clock. There is no need for complex clock recovery, everyone is perfectly in sync. Controlled environment, the distance is centimeters, the wires, traces on the PCB, are of perfect quality, and there is very little external noise. Direct addressing, the CPU can directly address memory locations or specific hardware registers. It's a closed, tightly integrated system. A prime example is the PCI Express, PCIe, bus used for graphics cards and high-speed SSDs. How this differs from network communication. Network communication is fundamentally more chaotic and challenging. Featuring on motherboard communication, bus, network communication distance centimeters meters to thousands of kilometers, speed extremely high bandwidth variable, generally much lower than a motherboard bus synchronous, shared master clock, asynchronous, no shared clock, requires clock recovery, data transfer mostly parallel almost exclusively serial environment clean, controlled, reliable noisy, unpredictable, errors are common hardware homogeneous and tightly integrated heterogeneous, connects devices from countless manufacturers, addressing direct physical or memory addressing logical addressing, IP addresses, MAC addresses, requiring protocols to find device error or control minimal needed essential, CRC, checksums, acknowledgements, export to sheets. In essence, motherboard communication is a private conversation in a quiet library, while network communication is like shouting a message across a crowded, noisy stadium to someone you've never met. The latter requires a much more robust and complex set of rules, protocols, to succeed. For the difference between checksum and CRC. This is a common point of confusion. The key is that one is a general category, and the other is a specific, powerful type. Checksum, this is the generic term for any mathematical method that uses a block of data to calculate a simple check value. The goal is to detect errors. The most basic form of a checksum is simple addition. For example, the internet checksum, used in IP headers, adds up all the 16-bit words in a header. Weakness, simple checksums are not very robust. For instance, if one bit in a word is flipped from a 1 to a 0, and another bit in a different word is flipped from a 0 to a 1, the final sum might be the same, and the error would go completely undetected. Cyclic redundancy check, CRC. This is a specific type of checksum that is much more powerful. Instead of simple addition, CRC treats the block of data as a large binary polynomial and performs a polynomial division operation with a predefined generator polynomial. The remainder of this division is the CRC value. Strength, the mathematics behind polynomial division makes CRC extremely effective at detecting the most common types of errors in hardware and transmission lines, especially burst errors, where several consecutive bits are corrupted. It is far less likely that a random corruption will result in a value that produces the same CRC remainder. Analogy, a checksum is like counting the total number of people in a room to make sure no one has left. A CRC is like giving each person a unique, numbered jersey and then running a complex mathematical formula on those numbers. It's much harder to accidentally fool the second method. This is why CRCs are used in high-integrity systems like Ethernet, Wi-Fi, and data storage, hard drives/SSDs. Excellent and nuanced question. You're touching on several distinct but deeply interrelated layers, local device clocks versus recovered clocks, internal bus protocols versus external serial links, and physical NIC to system data path. Let me give you a clear, layered, and raw breakdown. White heavy checkmark summary of critical points. Internal device clocks is not equal to clock recovery clocks. Internal motherboard buses, PCIe, SATA, etc. typically use shared reference clocks or negotiated clocking, not full-blown clock recovery like external serial links, example Ethernet over twisted pair or USB differential pairs. Peripheral devices, SSD, audio, NIC, etc. They use standardized communication protocols, example PCIe, SATA, USB, to talk to the CPU/memory subsystem. Each protocol defines how clocking, framing, addressing, and data transfer works. NIC physical connection, a NIC connects to the system via PCIe, internally on the motherboard, and connects to the network via Ethernet PHY, externally over copper/fiber. Main takeaway, clock recovery happens mostly on the physical layer between devices over external serial links, not inside tightly integrated, high-speed buses like PCIe, which have their own clock management methods like embedded clock lanes or reference clock sharing. White heavy checkmark full technical breakdown. Pushpin 1. Difference between internal clocks and clock recovery systems. Concept description: internal clocks, motherboard buses, devices like SSDs, GPUs, NICs internally share a reference clock source, provided by the motherboard or the CPU. Example, PCIe uses either a common reference clock, REF-CLK, or separate ref clocks with spread spectrum clocking, SSC, duck clock. Recovery, external serial links. When devices communicate over external cables, example Ethernet, USB, HDMI, DisplayPort, they embed the clock inside the data signal, self-clocking, and the receiver must recover the clock using CDR, clock and data recovery, circuits. So, motherboard internal PCIe lanes rightward arrow shared clocking. Ethernet/USB over cables rightward arrow clock recovery needed. Push pin 2. Do internal peripherals perform clock recovery? No, not in the same way as Ethernet or USB. Inside the motherboard, on PCIe lanes, for example, devices often use embedded clocks sent on a dedicated lane, or sideband reference clocks, but they don't need to extract the clock from the data stream. But some high-speed serial interconnects, like PCIe Gen 3/Gen 4, do implement equalization, de-emphasis, and clock compensation, but that's different from classic clock recovery. They do lane training, clock alignment, and data rate negotiation, but often assume a reference clock exists. Push pin 3. Are there communication protocols to manage peripheral devices? Absolutely. Every bus or interconnect standard defines its own protocol stack, covering layer examples: physical layer, PHY, electrical signaling, voltages, lane counts, PCIe, SATA, USB, link layer packet framing, flow control, example PCIe TLPs, transaction layer packets, transaction layer/command layer read/write semantics, memory mapping, interrupts higher layers, software driver level, device enumeration, configuration, OS drivers. Examples of major internal device bus protocols. Bus type used for PCIe, peripheral component interconnect express, NICs, SSDs, GPUs SATA hard drives, some SSDs USB external peripherals, mice, keyboards, external drives, I2C, SPILO speed embedded devices AXI/AMBA, on SoCS, internal chip interconnect. Push pin 4. How does a NIC physically connect to the rest of the system? On the motherboard, internal. Stage roll NIC chipset/controller sits on a PCIe bus, inside the motherboard, duck PCIe. Lane high-speed serial lanes carrying packets between NIC and CPU/memory subsystem. Device drivers level software that manages packet queues, DMA buffers, interrupts. To the network, external. Stage roll Ethernet PHY, physical layer transceiver, converts digital PCIe data to analog voltage signals for RJ45/copper or optical signals for fiber. Magnetics/transformers/RJ45 port handles differential signaling and ME protection for the actual cable. Ethernet cable transports the analog signal to the next hop, switch/router. White heavy check mark 5. Bonus concept, clock domains and crossing between them. Different clock domains exist everywhere. CPU runs at GHz scale. PCIe has its own clock domain. Ethernet PHY runs on a completely separate, link layer clock domain. Audio devices run at their own sample rates, 44.1 kHz, 48 kHz, etc. Crossing between domains happens through synchronizers, buffers, FIFOs, or protocol-defined handshakes. Example, T2 Ethernet data transfer rightward arrow PCIe transaction layer rightward arrow NIC memory rightward arrow NIC TX engine rightward arrow Ethernet MAC rightward arrow PHY rightward arrow clock recovery on remote device. White heavy check mark 6. Conceptual answer to what is the data across all this? At every step, the data is not the bits on the wire, nor the voltage on the lane, nor the light pulses. The data is the state transitions relative to an agreed temporal and protocol context, which requires a clock, a framing rule, a decoding rule, a shared higher layer meaning, like TCP/IP or HTTP. Without all four, you have no data. White heavy check mark strategic follow-up paths for you. Do you want a layer-by-layer breakdown, physical rightward arrow application, for a full end-to-end Ethernet packet? Or a deep dive into PCIe signaling and clock domain management? Or focus on signal integrity, SI, equalization, jitter tolerance, and SerDes design? Or the history and design philosophy behind different bus protocols? Let me know your preferred next rabbit hole.
The clock synchronization is also not something that only happens with peripheral devices, but it also happens when you have circuits that have different latencies. Because latency is the amount of time that the signal takes to travel from one place to the other. So if across the hardware the latency is different, then you need to have other internal clocks that are gonna basically divide the time and synchronize the time. And the internal, like the way that this is gonna happen is based on a specialized circuit that basically takes the frequency of the clock cycle and divides the frequency using basic math. I did some time ago, maybe I still have the code. I went over with GPT to build, so you can use this thing, like the way that they develop hardware nowadays is using a specialized language called hardware Verilog. And you can use this language to create simulations of hardware. So you build the actual circuits using this language. Then once you have the program, you have another program that allows you to model. And a lot of these programs are obviously going to be like either very expensive or closed source, proprietary of the hardware companies, because obviously it's very valuable and it takes a lot of time and research to develop everything. So you can't look at all, but there are some open source libraries that are similar to this. And basically you can code the circuits yourself using this, and then basically once you have the final file, then send the file to the company that is gonna use that file to basically feed the layout into a machine that is gonna actually print the patterns using the photoresist, and it's basically shooting lights at the photoresist to create the difference in heights that are gonna be equivalent to whatever geometry you encoded into the software. I don't remember. I think I might have either lost it or put somewhere else. But I do. Maybe I moved to the ether. I want to see because I went over with ChatGPT and we did up until the like I was gonna build the UART circuit, and like it guided me to. I didn't know he was doing that, but like it guided me to the sequence in the beginning to create this circuit that allows you to change the frequency of the clock, basically. I think it's hardware. Yeah, I think maybe I still have here. Yeah, Verilog projects. Yeah, I think I still have the code here. I don't remember because it's been some time. But now that I'm looking into this again. Also, I think I'm gonna look into the Onur Mutlu lectures pictures that I took. Because the other thing about this hardware topology and the network systems is that is obviously connected. So on the hardware itself, because of the latency, there are several different strategies to connect the components that are going to deal with the latency of multiple requests differently. But I don't remember the specific nuances of this. I do remember that like I think most topologies is basically going to be a grid where I have several different parts connected on the grid, and the grid is basically the communication bus between the signals. You can imagine at any given time you have multiple requests coming, so it's like the beats. You can imagine as water coming into the grid, and then you're gonna have to have algorithms and stuff like that to deal with conflicts of like multiple different paths coming together and stuff like that. I don't remember the specifics of this though. I'm gonna look to the resources again. I think review the resources. So basically, this is the language you use, and then there's another software you can use to actually see the waves. I forgot the name. I think I forgot. Maybe there is here. No, this is just the cache, I think, or the results after you compile. Makefile is the one that you build. I think the software is called Waves. Let me search for this again. Oh, it was something else, probably. I think it's GT Wave or something, GTK Wave or something like that. GTK Wave, yeah, that's the name of the software. And it's open source, I think. It's open source. You build. I think for Windows, yeah, this one. So for Windows, I think you download the installer. It's basically this thing here. So the way that you do it is you code the circuit on the language, then you compile, and then you can open on this thing here, and it allows you to see like the frequency of different things you put on the circuit. It's very interesting. Yeah, so you create registers like this. And this was building up to this UART, but I didn't finish doing. So the thing about this is that's not like it's a normal code, because it doesn't necessarily execute in sequence. Some of this stuff, like it's a different mental model you think about this. I think one of the files creates like the parameters of the simulation, and the other one creates the structure, I think. So I think that this one is the sequence of events, but this one is like you're creating the software represents the circuit. So it's not like he's gonna run in sequence, is that you're creating like the blocks, the digital blocks of the logic gates. Maybe it's the other way around, where this one is the the sequence, and the other one is the block. I think that this one is kind of like a function. Come on. Like, I think this is the test bench. This DB here is test bench. This should run tests. And this one is going to be, this one is the circuit of what's happening. So you can kind of like, it's basically the same thing as a function, but instead of thinking as a function, you think as this actual circuit of the logic gates. The clock determines like when the transitions happen between states. So like the best way to think about the computer is like a geometrical structure that is going to change its electromagnetic state based on a phase shift, which is the clock frequency. And that, so it's like basically a finite state machine with memory. It stores memory. Just a transition of states based on the geometry of the hardware that is based on the clock cycle. So here I have 3 wires. They enable reset in the clock, the out bits. So if it's on the reset state, this I think is setting the variables, setting the registers, I think. And what's the register? This counter here is a register, and you do like this when you want multiple bits, I think, on the same register. And then you have the output, which is a 1 bit, I think. So if it's enable, it's basically counting. Yeah, so you just do on a loop, I think, every phase of the clock. Yeah, so you have basically a control signal. Every phase of the clock you increase by 1 until you get to this threshold, whatever threshold you want to put. And then it basically clears out. It goes back to the start and throws the outputs. It's basically a loop with a sum. And that's, I didn't finish here, but I assume that that's what's, like, this is kind of like the regulating the clock frequency. So like imagine this clock has is at 1 frequency, and it goes inside of this loop, which counts in this way, which allows you to delay or change the frequency of the original clock. So based on this sequence of clocks, it synchronizes the different components of the hardware. And the name of this is URT, I think. Name of this process. I'm gonna put some music for myself and remove the sound. So instead of looking into these ones, maybe I'll go fast over these ones. This is just pictures of the struct on Linux, of the skbuff, and the SKE stuff is gonna be the code related to managing the network on the kernel. So it passes from the driver to the kernel. The kernel stores the request on the pool, I think. And then based on the processes are gonna ask for the kernel for the request on the pool, I think. polling states the stuff that I was talking about before. Just the device or like the algorithm, the system is going to do interrupt requests to the kernel. It's kind of always sending a signal, signal to the kernel saying that basically means that it wants the data. So now I'm going to go over the Honor Mutlu ones. I think I have them here. I was gonna do these other ones first. I think there's so many ones from Honor. I think it's probably this one. Oh, this is from a book. I don't remember which one is which. I think the fall one is the one that has the interconnection stuff. Or the number 23. Interconnects. And this one's very good. I'm gonna read this first. Oh, this is cache coherence. It's not gonna be protocol of communication. Or maybe it's at the end of this PDF. I do think that's it is related here. Interconnection networks. And the thing that is kind of confusing, it was confusing when I was watching, and I think it still is, about the lectures, is that I wasn't really sure if this is related to the hardware for communication. This is like the hardware related, for example, for with the NIC, or if it is more related to the communication between processes on the hardware. This is another common thing that the systems, like the data path from CPUs, when you have multiple different CPUs, they're going to communicate with this shared system, which is the interconnection network. And different memory systems also have basically the same thing for cache coherence and consistency, where they have strategies for communicating. The data banks have strategies to communicate with each other. So these lectures here, I'm not really sure if they are talking about the hardware specific to network devices or interconnect, or if it is basically the same thing. I obviously assume that the principles are going to be, if not exactly the same, they're going to be very similar. maybe you should review the communication on buffer or on the bus as well. I know that the like 8 entry point, the gate of each system is going to be a tri-state buffer, the logic circuit that does the gate. But I don't remember the synchronization of the bus. How does it work? I'm gonna ask that GPT, the buffer or the bus stuff. So obviously the way that I'm imagining this now is that this circuit that is mentioning here is just like the geometry of how the bits are gonna flow, but they don't process the requests. So the way it makes sense is that you have all these other systems that are gonna have other gates that actually do these calculations to parse the whole protocol, and that's why you have these several different layers. So each layer you're sending a sequence of bits. Then at each layer of the system, it makes sense of a portion of those bits. And the way you know the boundaries is the preamble. I'm gonna ask about this as well, now that I remember. So I think that this circuits here is just like the geometry of the that connects the external network with the internal memory of the computer. And then the processes on the data path are gonna be the thing that processes the makes sense of the bits. Like this is the thing that makes kind of confusing to understand. Is that the language that they use here? Like what the fuck do you mean by two packets trying to use the same link? Because like obviously if it's just a signal, like how do you know what is a packet? Like the hardware doesn't know what is a packet, it's just receiving beats. So it almost makes it imply that there's going to be a circuit inside of here that determines like what the beat means. Which has to be the case. So there's like control logic, control signals that determine what is a packet. But then it's kind of confusing. Like how does it, like what is the circuit and how does it know how does it make the distinction between what is a packet and what it isn't, and what is the difference between one packet to the other? Like how does it know that it has two packets arriving, not only one? That makes it kind of confusing to understand. The issue is that the like highest level of detail that I could find, at least for now, online is the other Mutlu lectures. And there are some other ones that like are variations, but they talk about it in different ways, but I don't think that they explain like the highest level of detail possible. And it's probably just because it's very hard to do, and because like it's not everything is open source, I think. I think it's just a hard thing to. I would need a lot more lectures if you're gonna explain every single detail. So what ends up happening is the same thing that happens with programming, is that everything gets hidden in abstraction, but then you lose the layers when you're explaining the higher levels. And the thing is that even though you know the lower levels of abstraction, in the context of the new level, is still kind of fuzzy. I hate when it does this. Because then I can use the... I guess if I select, it's gonna allow me to use the TTS. At this auto negotiation thing, there is a setting on Windows that you can change. If you go to your network configurations, you can see that you have the options there to change how they are gonna synchronize. I guess the reason why it's confusing is because of the boundary between the software and the hardware. Because I'm thinking about the situation from the software perspective. But if you think about it from the hardware, then it's very easy because it's just physically connected to different parts, like the devices. So the frames are going to be physically separated the moment that they get into the hardware that is going to connect them both. Like on the gates of the hardware, let's say, you're receiving the data on different physical lanes. And then inside of the hardware, there's going to be logic, which is the logic that I was going over here. Is basically the topology of the hardware, and the circuits of the control logic are gonna have algorithms as well running on them to like determine where to send the data of each one. So even though they're being sent at the same time, it still doesn't matter because it's separated. So, and I think like in order to reduce the, so like you don't have to use a bunch of cables to send the data, we're gonna use a multiplexer. So you just have multiple signals coming to the same place. The multiplexer is a circuit that allows you to determine what's going to be the output based on the input. So you can have like 4 inputs and 2 outputs, and then you have selectors connected to it, and the selectors are the things that determine what the output's going to be based on the inputs. And then based on that, you can encode like the signal. Even though you're receiving 4 bits, you can pass 2. And I think that's how they make it. So that's, so on both sides, one side you have multiplexer, the other side you have the multiplexer. So you have like, let's say 8 parts, 8 physical devices on the switch, on the network. They all go through the multiplexer, which combines the signal into one through this selector mechanism. And that's synchronized based on the protocol, which I think is going to vary. So there's going to be both the Manchester encoder and the other stuff to put the clock, combine the clock with the data to make sense of that. But there's also going to be the other things, which are the modulation, I think, and other stuff to basically synchronize the outputs of that signal with the inputs of the other device. It's going to receive the input through one cable, but then it differentiates based on the timing. And like the frequency of the signal determines which port it's going to go to. And basically, it's probably on the message as well, yeah. Definitely on the message. The bits on the message determine what parts is going to be receiving the signal. So the port is just the physical connection on the switch. And the multiplexer do the encoding and decoding of the signal across So it sends through one cable, but on both sides it allows you to have multiple different devices. Now it's a lot more clear to me. And there's also this. Maybe I'll. I think I'm gonna. There's a channel. I think it's demodulation, which is also very interesting, because what happens on the modem is that the modem itself is the structure of receiving an analog signal and then converting that to the digital signal, and that happens through the. I forgot the name of the. There's a region on the silicon that triode region is the name, where you can think about it as a boundary, like as a gradient of the signal, the electrical impulse. So when the transistor connects one type of material with the other one, it has this, like, at the edge of that is gonna be where the gradient of the electrons are gonna be changing in order to perform what is considered to be the 0 or 1 based on the voltage. So at that region, you can kind of shift that depending on the design of the hardware in order to allow you to amplify or amplify. I'm not sure what's the opposite of amplified. But basically modulate the signal based on that. So it's basically like parsing the noise, what could be noise, into a clear signal by amplifying these differences on the gradient of the thing. And what's the circuits that do that, I think they're called modulation and demodulation or something like that. There's a YouTube channel that he shows, but he talks about this, I think, in some other contexts of the Wi-Fi and radio signals or stuff like that. There's also, I think, they should watch so much stuff that I forgot where each thing comes from. There is a book as well that I was reading that explains that. Maybe analog to digital hardware design. I want to try to find on the subscriptions as well. What is modulation? This one. I want to watch this off stream. There's a lecture. Analog, analog to digital converters, ADC. Let's see if I can find the name of the guy or the channel. There's a channel where he shows the kind of like 3 blue 1 brown, but for this networking stuff. And he has some good videos about this, like short videos that are very descriptive. I forgot the name of the channel. I'm not really sure if he changed the logo. I'm not gonna be able to find. There was a specific name. Remember, like I found this channel based on a specific keyword that we're searching. If I go back to the hardware stuff, the hardware spreadsheet that I have there, yeah, I think I don't remember based on the subscriber list. I can find. I'm gonna open the spreadsheets that I have there. Something. I think it was this stuff here, digital modulation. Yeah, quadritude. Yeah, this stuff here. This is the name of the thing. Yeah, this is like, it's kind of like a circle that you have beats and then it allows you to code, decode signals. Yeah, it's this channel here. So I think this is another one. Yeah, so it's this one and this one. I think it's this one. And I saw. This is related to the modulation. To decoding this, but I think this is for Wi-Fi. But there is another one that, but this I think I found on the book that talks about the hardware on how the modem converts the actual signal that is receiving from the cable into a digital signal. It's basically changing this amplitude of the triode region to amplify the signal, and then you have a clear 1 or 0 based on the incoming thing. Yeah, I think, yeah, it's this one. I'm gonna watch this later again. So maybe I'm gonna search for molding hardware topology or hardware design. But yeah, this Fuse Lab has a lot of videos on hardware design, but I didn't like the videos that much. It's kind of hard to ground into the. Honor Motul lecture is a lot better on this style because it's easier to understand from a software perspective, I think. The Fuse Lab is more for like designing the hardware, but I think that he doesn't go into the details very much. Maybe I'm not understanding very well, but for me, it is not very good. The Fuse Lab for understanding the design in the context of the software engineering. I'm gonna search for this later. I think the best way is probably to go find the companies that produce the hardware and then go to their websites and look for the documentation. Then look at the actual spreadsheets of the hardware and like decode yourself how it works. So that's probably what I'm gonna do at some point. But it would be nice if there were videos about this. Yeah, like the guy explains on some video that I showed last time at the stream yesterday, is this phase lock stuff is just a loop, and then before the loop you have an XOR gate, I think, that connects the clock or the bits coming in. I don't remember. Maybe I should watch that again. Because he says that like one of the parts of the XOR gate has a resistor, I think, that delays the signal. And then inside of the loop, there is another thing there that captures the phase of the signal. And then once you hit the threshold where you want to synchronize the signal, then it opens the gate again through a control logic. But I'm gonna look into this again. And the thing is that like it doesn't. The video is very good, but it's just not like because I miss the context around the thing. I think. Ben Eater also has videos about this, about clock synchronization. Maybe I'll watch these videos again. So there's an edge detector, and then there is the loop there. The data edge. Data edge would be the mix of the clock with the data, so the transition between the states. The data, the edge. Maybe the edge here is the clock edge. So this is the data. And there's a delay here, and this is an XR. This PI filter and NCO. Yeah, so I guess it's like he doesn't explain this, so I should probably look into this as well later. And this is the phase, and then you adjust the loop here, adjusts the signal based on the whatever this modulation is, this frequency that is determined by these two components here, I think. Then when it hits whatever you want, whatever you program these things here to hit, then it's gonna send the signal. Just like a waiting room, let's say, that synchronizes based on whatever you want the signal to be, whatever frequency you want the signal to be. I'm gonna watch this video again. Has other videos as well that are very good. This channel here. And the best way is basically to go over these papers here, the actual implementation, or to implement yourself with Verilog, and then produce your own hardware basically. So you code the circuits, then you send the file with the design to manufacturer, and then they use the machines to create the hardware. But then obviously you have to invest money to do that. But the design obviously you don't, because it's open source. The language and some of the software to do this. But then obviously it's gonna take a lot of time. So let's see. I was gonna look into that. Yeah, I'm not gonna dive into this now because there's so many other stuff to do. I guess I'm just gonna go over the other spreadsheet from Honor, and I'm gonna stop streaming, watch all these videos off stream. And I think I'm gonna leave the Type Theory stuff for some other time. Because I'm gonna open up a bunch of branches. I was gonna ask about the bus as well. That's not true, GPT. Car Dump has a good video that he mentions or he explains briefly the tri-states buffer. But it's a video about something else, but he talks about tri-states or three-state, however you say that. Car Dumped. There's not new videos. I don't remember which one he talks about though. The three states. I'm gonna look into this later. Whatever. Okay, so I'm gonna stop streaming now. So yeah, see you next time.